Just so you all know, Jeremy Reese will be presenting now on concepts in material design to facilitate anti-gravity and advanced propulsion concepts, including research into ideas like metamaterials, bismuth, liquid metal compounds, and more. Jeremy, for those who don't know, is very well known for scientific and technology analysis on the Alien Scientist YouTube channel. He's been doing that for more than a decade. He has over 100,000 subscribers. And that is really the largest channel of its kind. He has tons and tons of stuff. The other thing I should mention to everybody attending APAC is if you're seeing this, watching live or you're watching it on YouTube, Jeremy does tons of midweek stuff. He has Mark, he has Jeremiah, he has lots of folks on throughout the week doing streams. So if you're watching this now, again, I believe it's youtube.com/alienscientist. Alienscientist.com is another place. And so I would definitely recommend, you could just Google Alien Scientist YouTube. You could find it there. I would recommend subscribing because he has a lot more there than we're doing just in this conference alone. So take it away, sir.
Yeah, Tim, to add to that, we're going to be expanding that soon and setting up a podcast studio and flying, people here if they're from out of town to interview them live in a kind of a 4K and a high def sound setting, and really get into nuts and bolts on work. And we're also have that in part with Mark at the Falcon Space Lab in New Jersey, where we have a lab to vet and verify and test various equipment and ideas. So bring your gyroscopes down or whatever you are building, and we will we'll examine it and do it justice with high def video and some real in-depth reporting. So without further ado, I will start my presentation.
Can you make it full screen?
Yeah, how do I do that? This is Alt Enter usually works for that, but Alt Enter. How do I make
check view on
yeah, let's do view present. Yeah, Control F5. Here we go. All right, so a little bit about me. I have a bachelor's degree in physics with a minor in math from Bridgewater State University. I went on and off for a number of years, switched my major to business management, then I switched it back to physics, and I eventually graduated in 2012. In the meantime, in between, I did a lot of work in construction and materials. I worked for Foxborough and Invensys doing some chemical engineering and got some end experience in industrial automation and control systems. I've been interested mainly in metamaterials and quasicrystals since about 2004 or so, when I got into researching those types of things and all this type of stuff in general. I'm basically a human resources coordinator, and I meet lots of interesting people, and I connect them and network them together with people I think that they'd work well with. And so I've just been trying to link together the people and identify the sources of good information, the sources of good materials, and good different knowledge and subject matter experts on various things to kind of piece this whole puzzle together about what we should be building. Take my money, love your channel. Since you were on the Timcast, thanks to Dr. Fox 2000 there in the live chat for giving me $10 in the live chat on YouTube. Sorry, I have to call these out, or people will donate more money to us to keep this thing going. So anyways, this is Feynman. He did a presentation called "There's Plenty of Room at the Bottom" back in, I think, the 70s, on nanotechnology and the future of building stuff on the small scale and what we need to do. And just to give you a scale, we can zoom in on this ice crystal several hundred times, and I think this is a magnification of what is it, scale of 1 nanometer to, I think this is just a factor of 100. But anyways, we're talking about the building blocks of nature. We all have the same building blocks. Assume that aliens have the same building blocks as we do. Except their periodic table includes all of the other isotopes, like all the heavier elements, not like heavy elements up here, but elements with an extra neutron, which change the isotope number without changing the element number. And we have a particle zoo, of course, in particle physics, the standard model, which is the best we have right now until a better theory comes along. We have up and down quark, charm, strange, top, bottom, this Higgs boson field that kind of like holds everything together and gives it mass. The Z and W bosons, the W has a positive and negative boson. Then we have photons, which is kind of like this electromagnetic force, and then gluons, which hold these nuclei together inside the nucleus. It's a really messy model, as our last presenter explained, and there's a lot of attempts to unify it through geometric unity and other such theories. One of such theory that I looked at was called Phoenix theory, the physics of entanglement networks and information exchanges, by a guy named Ken Griggs, who was studied under Sasha Migdal and Jim Gates, trying to relate string theory. And he related a lot of his research to Louis Kaufman, the mathematician, on knots and knot theory, and trying to come up with a new theory of particle physics based on knots. But regardless of how it all works under the hood, we still have the same kind of building blocks for our universe, to what we have to build with. So these are the isotopes. So like all these elements right here is just this black line right through the middle, and then there's all these isotopes on either side, showing that are stable. That, some of these aren't stable, and the further that you drift off, they just don't even exist. But these are everything we've pretty much mapped out, all the way up to these higher elements, which we're still mapping out. There's something called let's break down the periodic table so we can kind of like understand it a little bit better. We have all these non-metals over here, and non-metals are usually positively charged cations. Anions are negatively charged. So nonmetals are usually negatively charged, and metals are usually positively charged. They're alkaline. That's where they make batteries out of them and stuff. And the matching rules based on opposite sides of this table will base on what kind of things can match with what, and it's just all about filling these outer shells with the Lewis structure. But really, there's some interesting behavior right around here, because there's metals that kind of like are metalloids. They're not, this line right down the middle, like bismuth, silicon, arsenic, tellurium, and actinium. It's kind of like they're metalloids. They're not really metals. They're somewhat in between. And then there's also bismuth, which is kind of an interesting metal we'll get to later. But a lot of these metals have interesting properties, and we're going to go through kind of them. It's not as much as we try to classify them based on, they have similar kinds of properties based on this table of elements, like the families going up and down, and also the periods going left and right. But really, every element is kind of its own little building block, and it's kind of important to understand them they aren't seeing the presentation on that screen, so I have to switch. Hold up, I have to switch my OBS because they're not seeing the presentation on their screen. Hold up. Yes. Hold up a second. So display capture, I'm going to properties, and we're going to there. Boom. All right. So I fixed it. Sorry, they weren't seeing my screen before. Now they are. All right. So we have a bunch of these building blocks, and it's based on the size of the nucleus, how much mass is inside, and how much charge there is. Kind of gives you this whole Greg Chase just threw $100 in the super chat. Keep up the great work and don't give up. Bio Nerd said can't see the presentation. Also, when can I pre-order my Tic Tac craft? So yeah, this was the presentation so far. I wanted to show some of those slides to the audience out there because they didn't get to see them all. All right, so yeah, this was the Phoenix theory. This was the Higgs boson and all the particle physics. This was our table of building blocks. And that's me with some of my math professors on my graduation day. So metals versus nonmetals. Nonmetals form anions. They're dull, colorless to colorful. They're poor conductors. They're brittle. They have a low melting point, often liquids or gases at room temperature, and not sonorous. Yeah, so a lot of these things are actually gases at oxygen, nitrogen, chlorine, fluorine, chlorine, and hydrogen and helium. Of course, they're all really gases. I think the hydrogen's the smallest. I mean, helium's the smallest atom that there is, and size wise, but they all have different. They all kind of fit together in different ways based on their size. If you can kind of think of like spheres and sphere packing a little bit, but a little bit different. So these molecules and these atoms, the atoms we have in our periodic table of chemical elements combined, and I'm having trouble going through these slides one at a time, to form molecules. And molecules can be left or right-handed. So left and right-handed molecules that are opposites of one another are called enantiomers. And it's based on chiral symmetry, so they're the same in a mirror as the other one. And then there's chemical isomers, which is just basically they have the same chemical like composition. It's still C3H 6 H7F1 or whatever. It's still the same, but it's just a different arrangement of those things. And that's different than a nuclear isomer, which is basically like the isomers has equal N, equal A, and equal Z. So an isotope has the equal Z. We have the same proton number, we just change the neutron number. Isobars, that's equal A, which is I believe and isotones, and then so there's a whole bunch of different variations of nuclei and ways to change these nuclei around based on energy levels, and there's one that's an isomer that we know of. The lowest one we know of is actually hafnium tantalum isomer, and that one is the lowest stable one, and it actually switches between hafnium and tantalum. It will go back and forth because the numbers switch around or whatever. They can switch around, so they stay equal, but they interchange in a way. So we have nuclear isomers. Vibranium, I mentioned, that's kind of like what we mentioned by something that changes. It's actually like transmuting. It's an element that's transmuting stably, but you have to keep it stable by energizing it with gammas. And there might be ways to create more hyper stable elements by keeping them stable using isomers, but basically combining it with a gamma to keep it stable, because it has these decay chains through that decay into different things. So it changes so it can transmute readily based on those decay chains. But anyways, when we have mixtures of metals, and we have metals and all these metals and solids have melting points, and liquid, where there are things where they're a solid, liquid, and gas. We know about phases, and building things, sometimes require, changing phase of certain materials for different applications, mixing metals to form alloys. Metals are separated into two classifications: ferrous, non-ferrous. Ferrous is anything that contains iron, including like steel, and then non-ferrous superalloys, light metals like aluminum, magnesium, beryllium, titanium, cobalt, tantalum, and tungsten. Then there's non-metals, which can be used to make plastics, composites, and ceramics, including what are called refractories, like fire bricks and stuff. And refractory, the word refractory means it refracts light, so it can withstand really high temperatures like fire brick, and that's where refractory metals get the name refractory metals. And that's a section of these transition metals on the periodic table which have a really high melting point above 2000 Celsius and a really high hardness at room temperature. They're chemically inert and have a relatively high density. Tantalum, for example, is used. A lot of these are used in bone and transplants and like limb transplants, because they don't really cause what's it called? They don't cause inflammation. They don't cause reaction to skin tissue. Your body doesn't reject them. So a lot of those metals are used for that and other things. So these metals are a particular part of the periodic table that are of interest. Titanium, there's a Kroll method for purifying it that that they use to make this kind of sponge cake of different purities, and they take off the different pieces. But sponges are an interesting thing because it turns out a lot of different metals can be used to make sponges, and also other things like aerogel is a silica sponge, but it's like silica gel, but the gel's been replaced with air to make aerogel. And so these kinds of aerogels and aerosponges, including open cell and porous titanium, they're super interesting to research because they can pass air through them, and you could also possibly electrically charge these surfaces in different layers by printing them of different materials of different conductivity. So there's a lot of research that still needs to be done in these types of materials in aerospace. I think there's a lot of research that's being done, but not all of its public knowledge yet at this point. But certainly these aerosponges are certainly an area of interest to people who've done Biefeld-Brown effect or any kind of in just in aerodynamics in general, because they can be built to be custom aerodynamic. Tantalum kind of has this interesting structure as well, and again, it's really it has really good response to the human for implants and stuff. There's a mix of 1.6 tantalum to 1 tellurium forms a chalcogenide quasicrystal, which is a dodecagonal quasicrystal, a dodecagonal. A phase is, and it's distinguished by the presence of crystallographically forbidden 12-fold rotational symmetry in the diffraction pattern. So this is actually, tantalum can form quasicrystals. Some of these metals can form quasicrystals. This is one of the few that form it with a bimetallic alloy. Most of them are actually trimetallic alloys. You need 3 elements to form quasicrystals. Quasicrystals are pretty interesting stuff when you research them, because they have a lot of interesting applications. When I started researching these back in 2012, they don't have like a single fault line, so they could be made into really strong or durable materials, although we'll get into other strong durable materials and better ways of doing those a little bit later. What they're really interesting is their hypersymmetry, and that the fact that they have a symmetry on a higher level outside, but on the innate scale you can change individual parts and still maintain this greater symmetry. So they have a lot of application for photonic waveguides, 5D. There's also 5D optical data storage. It's not really quasicrystals. This is actually a nanostructured glass. I believe it's like quartz. And it's for permanently recording digital data using a femtosecond laser writing process. This is established technology. It's not theoretical. This is real. They've done this. The memory crystal is capable of storing 360 terabytes of data for billions of years. It has a really, really, really stable structure. It's really stable in these crystal structures, and can last really long periods of time, much longer than a floppy disk drive or a magnetic disk, or even a CD. First experimentally demonstrated in 2013. Hitachi and Microsoft have been developing this technology ever since. Quasicrystals are used. This is an Eric Quinones article from Princeton University. Their researchers built a scale model of a quasicrystal using a bunch of straws, and the straws were the length of the wavelength of microwave radiation that they shot out of this horn at it, and they noticed that it basically reflected those signals at 90-degree angles with perfect reflection without losing signal quality. So quasicrystals are certainly an interesting area of research that I think should be pursued further for future spacecraft engineering research. Of course, it's the little bit different than metamaterials, which these C-ring loop resonators that we talked about. What's interesting is that you can place the loops inside of one another to make a series of loops that each correspond to a different wavelength. So you can, this one will be like red spectrum. This is orange, yellow, green, blue, just to give a color code to get an idea of how this can be used to break down wavelengths and frequencies that come incoming into the craft. I'm not going to get into all of this stuff because I'm just going to give an overview of the materials. But again, yeah, they have built these resonator arrays with these split C-ring resonators. We believe there might be ways to do this on a smaller scale. Of course, when you get down to the atomic scale, once you get past a certain threshold, you no longer need the C-ring resonators, because what happens is the atoms themselves, actually, the spins of the atoms themselves actually kind of work for you if you use the right atoms with the right, properties. So there's also acoustic metamaterials. Just like, the structure of matter can bend light to its will, the structure of matter can bend sound to its will as well. Very interesting stuff. So this is like baffling that they use for soundproofing for recording booths and recording rooms. This is I think they place a microphone inside this pyramid and it can't hear anything outside the pyramid because it dampens and redirects all the sound through the material structure. This is the world's quietest room. It's at a company in Ontario, Canada. I forget the name of the company. It's in my notes. But there we go, notes. Yeah, it's the Eckel Noise Control Technologies. It's called ECKEL, the world's quietest room. There's also acoustic chiral metamaterials, okay, in nature. One of them is a seashell. You ever wonder why you put a seashell to your ear? You can hear all the air currents amplified, so loudly inside the seashell. It's because it's a metamaterial. It's literally a chiral metamaterial, and it works similar to the cochlea inside your inner ear for amplifying noises and sounds, and then into this sort of seashell shape, probably Fibonacci inspired spiral there. But in any case, the chiral metamaterials, there's a company Ron Kita runs called Chiralex that's investigating chiral quartz and some of these effects of chiral symmetry and chiral metamaterials. Some very interesting research, and definitely something worth checking out for future experiments and spacecraft engineering materials. Then we get into metallic beetles. So we talked about metals and nonmetals on that periodic table, but it turns out you can take purely organic compounds, nonmetals, and make them look like metals by etching them. And these are etched, biologically, but nature is sort of doing it in this case with these beetles and these skin coatings. But when we look at these different beetles under this SEM image, it looks like a series of dots and dashes. And it's just basically like there's no color or no tonation which makes it look like that. It's just basically the structures and how they interact with light on the skin themselves. It's nothing to do with the composition of the material itself. It's just the fact that it's not exactly metal. It's interacting like a metal because of its structure. So thank you to Infinitum Neo for the $100 super chat. He said, great info. Thank you so much. That's an awesome help, man. This is great. So we have, we find out that if we etch, University of Rochester, a guy named Dr. Chun-Li Guo is doing research into materials, and he found out that if you etch these materials with a laser, do laser etching, micro and nano pitting, similar to these nano pitting on the bugs, but you try different, patterns and different shapes, which we've learned from looking at the bugs. This one makes gold, this one makes this iridescent green and whatnot. They're actually able to engineer materials that are hydrophobic. So they're tuned, these spacings in the microstructures are actually tuned to water molecules specifically. And then they can do it to make them hydrophilic. So phobia means hate, philia means love. So hydrophilic materials are materials that love water. And you see how it goes right to the edge and sticks right to this material. It goes right off this, you know, super hydrophobic material in the middle. Most hydrophobic coatings that exist on the market presently work on chemical deposition of a layer of material that has this effect. When the polymers dry out, it creates a surface very similar to this. This is the only no application I know of where they can just laser treat a metal to give it this coating, which is really, really awesome to think about. So so the NOSA in the chat says there are better methods for super hydrophobic and super hydrophilic. Yeah, I'd like to check those out, but this one I just thought was cool because it relates to, you know, we can do the same thing. If we laser etch these sort of patterns, we can make it look like this bug, or that gold color, or the green color, or whatever kind of color we want it to look like. And I just thought that was interesting. And then the application for if you take epoxy thin films and then etch each thin film and then apply them in layers, they're tuned to different layers. You can make dielectric mirrors, which we'll get into in just a second, right down here. But we'll talk about, you know, yeah. So I'll just get right into the dielectric mirrors, and then we'll go back. So we have something called Bragg diffraction when when incident, you know, light hits a crystal or a structure, and different frequencies transmute or go into the material at, you know, have different penetration depths, to different have different interactions with every material. So certain frequencies will bounce right off the surface of the material, and some frequencies will penetrate deeper into the material, and then bounce around, or sometimes they don't reflect back. But what a Bragg mirror does, or a dielectric mirror does, is it tunes each one of these layers to those next frequencies, so that when they bounce off, all these frequencies sort of bounce back off. And it's very interesting what you can do. So examples of these are called dimensional crystals, and that one would be a 2D or a 1D crystal. So that would be a 1D. See these layers? So that's called an example of a 1D. You add these wafers and it creates a 1D optical dimensional material. And then if you get a 2D one, would be example of the surface, which is just like this. This is a forest of carbon nanotubes, and that's what Vanta Black is. That stuff Vanta Black is literally, it's a forest of carbon nanotubes. It's like a carpet of them, and the carpet of these nanotubes, it basically absorbs all the light that interacts with it, you know, or not all of it, but 8, 9% of it, you know, a ton of it. So I think it's like 90 something percent of the incident light it absorbs completely. And that's an example of a 2D dimensional crystal or optical metamaterial. And then they have 3D ones, which are more complex, which are those like quasicrystals and those other structures that we should be building in the future to run all of our electronics off of, because we don't need to push electrons around anymore. We can push photons around, and we can build circuits that work on photonic energies and the alignments of these spins of carefully aligned atoms and molecules along the circuits. Once we are able to build that small and do those kinds of things, and it's all based on waves and waveguides and mirrors and understanding that sort of technology, but on a intricate atomic and scalar lattice level. And that's the level as small as we can go. If we can go that small, we're dealing with, you know, it can't get too much closer to alien technology until we get into the other building blocks. But it's basically chemistry all the way down, regardless of how it works under the hood in the land of unification field theories. We know a lot about these kinds of materials. So next thing is shape retention alloys that I wanted to mention on here. Shape retention alloys are important because they can deform and like you put it in hot water and it will go back into shape. Like nitinol wire, you can deform it any which way. You throw it into hot water and it goes back into shape. And it deals with these, you know, austenite and martensite phases and how it can deform and go back into phase. And it's interesting because it's just all about how certain molecules and certain types of atoms linked together on this core, on this fundamental level. And as we learn more about that, we get to the topic of metallic glass, which is a real anomaly and almost a strange thing that almost shouldn't exist. But we talk about metal structures and the structures of just how things form in general. And things can form in crystals, or if it cools really slowly, it all kind of it forms like a hard crystal, and this is what's called the solid state. Amorphous structures are like solid state, but they have like a 2% elastic limit, which is higher than any kind of metal or any kind of solid material. So they're really, really flexible. They're much more, wood has an elastic limit of 1, for example, and polymers have, elastic limit, or, upwards of, 2.7%. So it's right around there. Plus it's got really high strength. So glass alloys and metallic glasses are really interesting, remarkable materials. I once compared them in a video to the Roswell memory foil that they talked about, that unbreakable like material that you could crinkle it up into a ball and it would unfold itself. Although I haven't seen any material exactly like that, any metallic glasses exactly like that material. It is an interesting material. There's a video on liquid metal tuning forks that you guys can watch. Liquid Metal Technologies is a company that makes these. I don't know why that one didn't load. All right. Oh, this one's important. So this graph shows you imaging and tweezing, and talks about, the length of tissues and organs and cells. We can use, MEMS and scanning electron microscopes to kind of see on that level. Then we can use optical and magnetic tweezing to kind of move things on that level. And then, when we kind of want to see below, cells and into proteins and maybe even into atoms themselves, we got to go lower. But we use one of the types of tomography is GPR and ultrasound imaging, which ultrasound, uses really high frequency sound waves and takes the bounce back, and they can use it to image things that are inside of, like the baby inside of its mother, or also ground penetrating radar to see pipes and other stuff that's buried underneath the ground. It's also very nuclear magnetic resonance imaging. They put you through a giant magnet, and they use this tomography to basically create an image of you in slices, and then add those slices together to get an image of your whole body. And that's kind of like, it started, there's a whole thing on tomography if you look it up. I had a whole page on it, but there's a long list of all like the history of the machines and where the technology's gone over the years, and the methods and stuff. But what we're getting towards is, optical tweezers and all this stuff. What we eventually want to get towards is, that the fact that 3D printers will be known as ancient replicators, and we want to build, this replicator from Star Wars. There's a couple things about that. We're not quite building a replicator with 3D printing. 3D printing has its limitations, called additive manufacturing. Certain things are still better to build on a CNC and milling machine, and out of a cast solid piece, because it's a lot stronger than something that's built up of a bunch of stuff that's been printed together. Something that's cast as a whole and then cut and reduced down through reductionist machining is sometimes better, is clearly superior than a lot of these other things. And also, this would be limited to, physical objects in your 3D printer. You could, I don't think they'll ever be able to 3D print you a frog or a biological living organism, or even print it something this fast, to come in. So, but who knows? The future may hold amazing things. But in any case, that's kind of what we're building up to. But we got to keep it within the realms of realistics. Composites are fabricating materials that involve mixing a metallic alloy in a solid state with reinforced particles or porous mass, and then infiltrating metallic alloy in the semi-solid state. So you can also mix different alloys with nonmetals and stuff. Lots of different, you know, expansion room and inventive ideas for composites, and lots of room for invention there. Carbon is, as we all know, is one of the building blocks that we definitely need to pay attention to. You and me were made out of carbon. We wouldn't be here if it weren't for carbon, DNA, and all our life forms. We love carbon because it forms really long chains, and really long chains are useful for building stuff like DNA and humans and little kittens. So we love carbon. It's also stuff we burn, hydrocarbons. There's a lot of energy in those bonds, so we use it for fuel. And it's currently the biggest fuel source on the planet until one of us invents free energy. So definitely carbon buckyballs. So there's a bunch of different Buckminster fullerenes. There's bucky tubes that can be formed from rolling graphene sheets into tubes. Graphite, of course, can be made into graphene through the Scotch tape method or electrostatic confinement and other methods. But there's also printable, we know that carbon can be made into diamond. That's another isomer or type of, is the diamond shape. So we can arrange, if you pack lots of carbon really close together, you heat it up and you pack it real tight, you can make diamond. There's also printable diamond, this stuff called polyhydridocarbon, which it's called, or PHC. It's a polymer that may be readily fabricated into various forms like films, fibers, plates, and then thermalized into a final hexagonal diamond ceramic. Upon thermolysis in argon at atmospheric temperature and pressure of 110 degrees Celsius to 1,000 degrees Celsius, decomposition of polyhydridocarbon results in hexagonal diamond or Lonsdaleite. Lonsdaleite, as you know, it's a translucent diamond. It's harder. It's about 58% harder than a diamond, a natural diamond. And, it's produced through by a number of companies, synthetic diamonds in a number of different ways. This is from Genesis Diamonds. And this is Genesis Diamonds Laboratory and their methods for manufacturing diamonds. And the high pressure types of environments that they use for that. Carbon chains, yes, as we know, they're pretty much define three huge realms of chemistry just on carbon alone. So it's very important for chemists. Biological, inorganic chemistry, and organic chemistry are all directly related or linked to carbon and what can be formed with carbon. The other one right under carbon, of course, is another key building block, just where it sits on the periodic table. It's just in the middle, straight down the middle of everything. So it kind of it branches off to everything if you think about it, where it sits on the periodic table. Same with silicon. Sorry, it'd be important to make this distinction because it's really easy to say the wrong thing because silicon is the element. That's what they mine out of the earth. It's the second most abundant element on earth after oxygen. Silica is quartz or glass. It's actually silicon dioxide. It's produced from the reaction between silicon and oxygen. And there's silicone, which is produced from the reaction between silicon, oxygen, carbon, and or hydrogen. And it's a kind of like a gel or, the silica gel is silica. And then, so yeah, it's very confusing, but I think we straightened it out. So high melting point, high boiling point, bluish grain, middle sheen. It's used in semiconductors and computer circuits and other electronics. Of course, if you take silica gel and replace the water with air, it makes aerogel, which is really heat resistant and fire resistant. It's good, fire block material. It's also got very good compressive strength. Not that it will cut with a knife. It's not, super strong or rigid material, but it will support some weight. And then there's also graphene aerogel, which is just basically like graphene, but in an aerogel form or with lots of gaps or air between. And there's even, 3D printed lattices of this to make it even more even lighter. And there's lots of applications with graphene aerogels currently. Dr. Tianyu Li at Lee's lab in the University of California in Santa Cruz is doing work on 3D printing of three-dimensional graphene aerogels with periodic macropores for supercapacitor electrodes. There's also another number of universities doing experiments with nanoporous graphene membranes and also, graphene channels that mimic or replicate the action of biological ion channels, so they can open up or these pores in the surface of these graphene sheets to let different molecules of different sizes through, depending. But in any case, then we have 3D graphene, base sensors and piezoelectric switches. So they have these graphene structures that when they press them together, they create these electrical switches, or also piezoelectric voltage, needles, whatever, pressure sensors, if you will, through piezoelectric action of the graphene, which is also interesting application for the graphene. Is it the wonder material? We've all hailed that it was. I think so. I think that, anyone who sort of underscores the virtues of graphene hasn't really done the research, and it's really underfunded right now, as far as I can tell. It's strong, it's thin, it's conductive, it's truly two-dimensional, it's stretchable, and it's multidisciplinary and it has a lot of applications in a lot of different fields. So I just believe we haven't even begun to see the full extent of applications of graphene yet. And it's definitely a technology that we need to consider in our experiments going forward and in the future. Piezoelectricity, of course, it's exhibited in graphene, but we all know it came from quartz originally, or PZT, lead zirconate titanate. Same kind of idea. That's the interesting stuff. When you vibrate quartz or tension and compress quartz, it produces a voltage. And well, yeah, graphene's cool, but there's lots of other stuff out there that we're looking into and stuff, as well as graphene. So then we'll get into it. So let me continue. Ferroelectricity, spontaneous electrical polarization discovered in 1920 in Rochelle salt by J. Valasek. Okay, so he made this Rochelle salt. This is a large crystal of Rochelle salt that was grown on Skylab. It turns out that if you grow this salt in zero gravity, the crystals that it forms are much more ferroelectric than the normal crystals grown on Earth. And so that is just some of the research that NASA and other organizations have done into crystal growth in space, and a lot of it's based on these materials. The ferroelectric materials led eventually to the discovery of nonlinear optical materials, these multiferroics like barium titanate, which we'll get into in a second. Ferromagnetism, of course, is just a magnet. It has a natural, iron, like natural iron is ferromagnetic. That means it's like a permanent magnet, just naturally. Paramagnetic means it will line up and become a magnet as soon as you put, any kind of a magnetic field on it. So like an iron bar that's not magnetized is paramagnetic. It will become magnetized. But if it's already magnetized, then it's ferromagnetic. And if it doesn't get magnetized at all and it's completely inert, then it's diamagnetic. And then ferroelectricity is kind of like the analog between ferromagnetic and ferroelectric. It means it becomes electrically polarized within a field if you apply a field to it. And these curves right here, see these curves? Those are called hysteresis curves, and we'll get into those in a second. Talk about those because they come into play. The transistor, diodes, and solid state physics goes back to Walter Schottky and also those guys at Bell Labs who invented the transistor. They were doing a lot of the theory on solid state physics and group theory, and essentially the core physics into how to build these kinds of materials that were used to build the first transistor. That did not come from aliens, as Philip Corso says. It definitely came from human scientists working on it for decades before that, and it was all it's all there. So cold fusion is kind of related to these metal halide lattices. I had to throw this in somewhere, so I threw it in here. I apologize for that, but metal hydride lattices like palladium, in cold fusion experiments, they put heavy water plus an electrolyte, and then they charge this cathode, a palladium cathode, and there's a saturation point of about 94% deuterium to palladium that you need in order to see the reaction, according to Mitchell Schwartz and the MIT guys like Peter Hagelstein. Mitchell Schwartz was the experimentalist doing the research on cold fusion at MIT, who I talked to, and came up with this along with several other scientists who have working in the field, who have kind of agreed that MIT replications were down here around 0.86, 0.88, where they've gotten no results. And so they didn't get their loading ratios high enough within their crystal lattices to achieve what we've reported, or what numerous scientists have reported as fusion actually taking place in the lattice structure of these cells. There's physics that can explain this. There's a new theory out there there's several theories out there with physics that explain kind of how these reactions can take place within metal lattices based on lattice effects, and also like vibrations and Bremsstrahlung radiation, Cherkanov radiation, and other ways of sharing sharing an excitation across a lattice. And so that's what allegedly takes care of the gammas in these experiments. Interesting stuff. But again, that might have some relation to, again, it's not really it's not really apparent how we can use cold fusion to get energy technology out of it yet. But I'm sure that through material science and maybe some of these experiments, we'll be able to direct that energy and those lattice vibrations from cold fusion, and maybe make some sort of device that can actually utilize that energy instead of losing it all to a lattice. But in any case, more work needs to be done in that field, and more research, I believe, because our spacecraft is, of course, going to need an energy source, and pound for pound, cold fusion is a real good bet for fuel source being abundant in water, and the energy output that we get from it. So, in any case, we'll talk about perovskites and high efficiency photovoltaics. So it turns out that certain types of materials work really good as photovoltaic materials. And those metal halides tend to work really good, but perovskites are probably one of the best. And they're used to make, bismuth ferrite is currently used to make some pretty heavy duty solar panel material and solar cell material. But through material science and construction of lattices, we might be able to effectively make this kind of stuff even better. And we'll talk about that in a second. Bismuth, the most diamagnetic element, it has the highest, it's basically the spinniest, has the highest spin. Nuclear spins in magnetic resonance, this kind of where the material world meets the quantum world. It's an interesting realm to play around with. And I think that, as we're learning with some of our research into Alzafon, who I mentioned here in a second, it's definitely something that the aerospace companies and the government and military have looked at as far as a source, understanding atomic spins and atomic spin orbits of these materials. It's definitely has something to do with it. We've investigated a material called spin glass, another one that it's basically like a glass, but you are injecting these atoms into the surface of this material, which have these aligned spins or predestined spins, or even materials which line up to the spins readily. And so that you could basically create like local magnetic monopoles, even though it won't be a real magnetic monopole. You could almost create local ones on the surface of the craft through these, really, strange electromagnetic effects, which would appear on the surface of these craft if you could coat them with spin glass. And, these spin and advanced optical glasses, it's basically like you're condensing light and matter, but also there's you create what's called a Fermi liquid. And Fermi liquids are quite interesting. It's similar to a Fermi gas. It hits this this sort of critical point with temperature and pressure, where along this curve right here, it stays classically critical. And this is all in Landau's Fermi liquid theory, which you can look up. But it's basically a whole new state of matter that is yet to be explored. It's very cutting edge and new, and it might be some interesting things to explore in there. Mercury is another interesting thing. Of course, it's very dangerous. We mentioned about doing some experiments with mercury earlier, and there are a number of groups out there currently looking into do some experiments with mercury. We've all heard of this nuclear powered flying triangle that Ed Fouché talked about in 1998, although maybe some of you haven't yet, but he was the guy that came out at IUFOC in 98 and talked about this flying triangle craft that spun mercury plasma doped with a bunch of other earth elements and whatnot. And he also talked about quasicrystals and metamaterials, which were really before a lot of the research was being done publicly into metamaterials or quasicrystals. It's really hard to find references to any of that stuff pre-1998. But he's a guy that worked at all the right places to have been out at Area 51 back in the early 80s, late 70s, and seen some stuff. And he's certainly an interesting guy, even if he doesn't have a lot of evidence to back up his stories. It's unfortunate. That's sometimes what we have to work off of. Of course, doing some research into rotating mercury, spin gravity research, we came across a guy named Henry William Wallace from Valley Forge, Pennsylvania, who was a General Electric employee, and apparently he had said some of these ideas about his anti-gravity thing with rotating mercury to some friends of his at work, and he had he actually patented an idea on it. And it turns out that the military was also, doing research into and had built his patent and were researching his same idea for this kinematic effect or gravitomagnetic field. And we had talked about this tokamak reactors being repurposed for some of these experiments on plasma currents. And because plasma is it's like the fourth state. It's the fourth state of matter above a gas. So you have an extra degree of freedom. And there's been a lot of research into what plasmas can do and different types of plasmas. And you mentioned red mercury as being, I think, who was that? Evan, was that Ronald? Who mentioned that? Sorry, I forget who it was earlier that mentioned it was barium titanate in the red mercury, but it might be other things. It could be also a liquid alloy of mercury, ammonia.
Paul Murad.
That was Paul. Paul Murad said that red mercury was was mixing some barium titanate in with the mercury. We might have some interesting effects.
Also, plasmas have some plasmas are near superconductors.
Interesting. Yeah. So this again, this ferroelectric hysteresis curve of where you can pump energy into the electric field and the polarization. There's a paper from 1966 on superconductors and gravitational drag by Bryce DeWitt, which is also interesting, showing that some of the theoretical work that was being done as early as 1966 into superconductors or rotating plasmas and gravitational drag, and trying to understand gravitational drag and in terms of these really large weight rotating, it's kind of like your flywheels that you guys were building, but a really, really huge flywheel, so I believe this was related to Boeing's Alzaphan anti-gravity study of 1981 with rotating nuclei and nuclear orientation as a concept for affecting gravity. NASA had a gravity probe B. They were experimenting with the frame dragging effect of this satellite as it went around the Earth. And apparently their results were positive. There is frame dragging. There is an effect. So it's quite possible that if you have your atoms aligned as little gyroscopes, there could be some kind of a similar frame dragging effect or gravitational effect. So that's an area for investigation with materials as well, which is why I included it. The next is barium titanate crystals. Barium titanate, super interesting. Barium titanate was actually discovered where they were doing a lot of research into the ferroelectrics and ferroelectric materials, super ferroelectric materials like barium titanate. So it becomes a photorefractive effect. So the photorefractive effect is a nonlinear optical effect, and it's seen in certain crystals and other materials that respond to light by altering their refractive index. So this material actually alters the refractive index of light. The effect can be used to store temporary erasable holograms and is useful for holographic data storage. It can also be used to create a phase conjugate mirror or an optical spatial soliton. These are all really important, key things if we were to understand light gravity as a field of the electromagnetic field, as a part of the electromagnetic field. Because these nonlinear optical materials will teach us ways to kind of trick light and possibly ways to trick gravity if gravity behaves anyway similar to light or on frequencies that can be operated by, say it's all light frequencies at once. We understand, some of these concepts combined, we might be able to build things that can, break optical gravity by recreating the spatial holograms. If gravity is kind of like a hologram, we can recreate a spatial hologram for the craft and kind of break gravity using these spatial holograms via these phase conjugate mirrors, which are really interesting materials. It's like a mirror that, wherever you turn it, no matter which way you turn it, you're always seeing your reflection on the mirror. It's always, you're always bouncing it back to you're always looking at yourself. And they're used in this experiment right here on phase conjugate mirrors. I want to play this video. I'm going to go find this video and play it real quick.
Isn't the phase conjugate mirrors what Apollo left on the moon for detecting the distance to the moon?
That was a little different. That was actually it was a special kind of a mirror array, and it wasn't. I'm not sure if it was a phase conjugate mirror. I'll have to look into that, Mark. I'm not exactly sure. It might be. You might be right. I'll have to look into that.
I think it was an array of mirrors at 90 degrees. So it made that effect. The light would bounce up from one mirror to another. And no matter which angle you came at, it would shoot right back to you. Two right angles.
Yeah, that makes sense. It probably was. It would be easier to target it that way if it was phase conjugate. Yeah, because then they could target it much easier. They probably did make it like that. But yeah, it just goes to show you, like, little things like that we're not told to the public. They're just like, yeah, it's just a mirror up there. But they wouldn't give you these little details. A lot of these details were classified for many, many years as this research was being done. So it's good that this is all coming out to the public now about this. So this is optical technology. They show this the hologram of the face. I forget who the guy is in the hologram. I think it's Max Planck or something. But so they find the focal point, and that's where they put the beam splitter, right at that focal point. So this mirror is reflecting this, it goes this way and then it reflects back. So now it's not reflecting anymore with this. They put this cup over it. It breaks up the beam and messes it up. It's because it's got like frosted glass. And then they take this conjugate mirror, and see that they twisted it, and they twist it till it goes into phase, and it has to, like, it goes into resonance. And phase conjugate mirrors only work at resonance, so that phase conjugate mirror is tuned to that laser frequency. And you see how that happened. It tuned rather quickly. It didn't come instantly. That mirror didn't reflect the image instantly. It sort of, it resolved it slowly. You see that, how it came? It didn't come on in instantly. It kind of like, it took a second to resolve the image, because it's literally doing optical calculations, which is why I was like, you know, I suggested that, you know, Jack Sarfati in our other lecture, that his a lot of these calculations that he's talking about could be done optically with the right optical materials, and this is what I'm talking about. So this forms a diffraction, and all this, it breaks up all the light going across there, so it all bounces all these different directions. Now that mirror literally has to find back all those paths through the glass to find the exact paths back, but it eventually resolves them all through optical computation, and the image comes into resonance and resolution on the screen. So if we can think of gravity as an imaging, you know, an imaging technology, or an optical imaging technology, using the right kind of phase conjugate mirrors, which again, this phase conjugate mirrors are tuned to that frequency of light. So if we can build phase conjugate mirrors which are tuned to the frequency of gravity, we could potentially trick gravity into the illusion of or hologram of that it's in a different spot. And one way to potentially do that is through what's called four-wave mixing. Interaction between three wavelengths produces this fourth wavelength, and then you could use that fourth wavelength as a pump beam. So it might be possible to resonate at the frequency of gravity using, you know, phase conjugate mirror materials applied to a surface of our craft in the right way, and in conjunction with four-wave mixing, so that we could, you know, use that to bend the local fabric of space-time, as we're trying to do with these skin coatings and skin structures. So ideas were a couple different things that I wanted to mention as far as chemistry goes, and with the types of chemistry and physics that we need to be looking into. I believe are plasmon polaritons, phonon polaritons, which are vibrational lattice, you know, vibrations, polaritons. Then there's exciton polaritons, which are excited states within the material. Then the Cooper pair polaritons, which are like those like magic angle graphene and some of those other types of materials where you line up these states to create these Cooper pairing, and in superconductors. Even in superconductors you have sort of Cooper pairing, and there's a lot of interesting things you can find on polariton condensates with superconductors. Of course, closing the terahertz gap is going to be a key thing for our electronics, and merging our light with photonics. But these exciton polaritons and polariton chemistry, there's a channel I found on YouTube called Polariton Chemistry Webinars, and they're doing a real good job of teaching some of this stuff, much better than I am. But I'll have to refer you to their videos. But we have nanoplasmonics, which is these polaritons, which are basically like a material waveguide that traps light. So light goes into a material and gets trapped in a material, and then if you pump this material with enough light, it builds up really heavily, and you can create negative mass. Here's an article on negative mass and a new way to create lasers at University of Rochester using these pumped polariton states. And these a lot of these sandwich materials are being investigated. Graphene sandwiches, and you know, graphene layer sandwich between two other materials, or two graphene layers of bread with superconductor in between. There's been room temperature superfluidity in a polariton condensate reported, and room temperature exciton polariton condensate and lattice. So it's a very easy way to do condensed matter and condensed matter light coupling. It's it's much easier than creating Bose-Einstein condensates or a lot of these other kinds of more exotic matter states that have been done in laboratories. It's easier if we create these sort of layered sheets and these layered materials the right way. See, these are the graphene sandwiches I'm talking about. They put this one has a superconductor in between. This one has I forget what they had in that one. This one's got calcium atoms and stuff, but they're basically a whole bunch of stuff that you can find on 2D layers of graphene with various materials sandwiched in between. And twisted bilayer graphene is also a thing. When you get to a magic angle, it becomes suddenly superconductive along one axis, which is super interesting. Learning intricate things about how to exploit quantum mechanics using materials. I wanted to talk about, I mentioned David Perez in this. He's building a spacecraft with this technology he's testing, and he's using, you zoom in really close on his circuit boards. These are snowflake. These are like Koch snowflakes. And there's a guy named David Cohen, Nathan Cohen, I believe, Nathan Cohen. And he runs fractal antenna systems where he builds, he takes these like Koch snowflake patterns and does like, numerous iterations on them and finds that, when he builds these antennas based on fractal patterns, they get, they tune in, they become metamaterials basically, and they become super resonant. And I guess this is what he's trying to do with this. Although, you could, I suppose you could do this a lot better. You could do a lot better than this. We could do a lot better than this, and we should be doing a lot better than this. Another thing worth mentioning are flying donut pulses. Schematics for, they're also called spatiotemporal optical vortices. So if you want to look up, sometimes they change the terminology on these things to obscure them and so make them harder to find. But this is a schematic of a metamaterial generator of flying donut pulses. Concentric rings of azimuthally oriented linear dipole resonators with spatially and frequency dependent scattering properties led to the emission of a toroid single cycle flying donut pulse. The resonator in different rings exhibit a different frequency dispersion. See the inset. And so the temporal and frequency form of the single cycle radially, sorry. I can't read the rest because this thing's in my way. But in any case, oh God, and there it goes back as soon as I try to exit. All right, never mind. Screen. Oh. No, that's not what I wanted. All right. Hold up, I'm trying to present. Okay. No, I'm way up here for some reason. Hey, man, it skipped a bunch of slides, I swear. Let me just make sure I didn't miss any as I go back down through this list. Oh, come on. I'm not using that mouse wheel. That mouse wheel's cursed. All right. So materials engineering, optical materials, and now we're getting down into these layered types of two-dimensional materials, also two-dimensional waveform materials, shaping their materials like waveforms. Then these really interesting flying magnetic donut pulses things, which are kind of an anomaly in physics. And then also holographic Higgs, scalar light matter coupling. There's some interesting papers on light scalars in composite Higgs models, and also light matter coupling with the Higgs boson and Higgs mechanism, which is the gravity field itself. So when we talk about light matter coupling, we're talking about trapping light inside of these metamaterials, producing polaritons, and then what are also called time crystals. So this is kind of relates to the those amorphous metals in the metallic glass and these sort of bendy resonant structures, and the idea that our UFOs are shaped like a bell or a saucer, or a symbol for a drum set, you know. So this symmetry and this sort of metal shape is ideal, I believe, for creating, you know, matter resonances. And when you have matter that's oscillating or resonating in time, and then you have that matched to a light coupling with these two light waves canceling to create a scalar light field in conjunction at the same frequency of your vibrating surface of the craft, you could produce what are called time crystals. And time crystals could be used to create, you know, basically, you know, gravity, warp drive. And this might be kind of, you know, where we're going in the future with these nano coatings and these nano technologies and stuff. And I had that as the last bit of my presentation, but I will end it with a quick jump over to Battel's website, who just got, and Battel was just awarded this $46.3 million contract to support manufacturing of materials for extreme hypersonic environments. So these are the skin coatings for these Mach 5 plus craft that they're admittedly developing, although, you know, I think it goes a little bit beyond that, especially with, you should realize it goes a little bit beyond that with some of the stuff that we covered in today's presentation on materials. And I hope there was, I'm sure there's lots of stuff that I missed, and let's bring that up and let's get some comments and questions and discussion on some of these ideas and some of these things.
Okay, well, Jeremy, it's Tim. Let me jump in real quick. So first thing, and again, we owe you an applause. I'm going to put it on gallery. Oops. So you know what? Let me here. I'm going to stop your share. Yeah, there we go. And everyone, this has been tremendous. Over 100 slides. So amazing, amazing. Jeremy Reese, the alien scientist himself, with one of the biggest channels, and he's presenting at our conference today. Thank you, sir. You know, I was taking notes that whole thing. Actually, I wasn't familiar with a ton of that stuff. So wonderful. I will definitely be coming back to that when we get it up on YouTube.